Hi, Stuart here. Today, consistent hashing. I've been wanting to talk about consistent hashing for a while because it's a very useful enterprise pattern for being able to allocate keys in a consistent way across a group of resources. So it could be fanning out to a database. It could be assigning work to servers, assigning files to storage, whatever. The problem with most hash algorithms is that if you grow or shrink the size of the hash space, you have to rehash a fair number of the keys, and that's less than efficient. The point of a consistent hash is that if you add or remove hash locations, that most of the things don't move. And if something used to hash to say node 3 and node 3 is still there, it will rehash to node 3 every time. I was trying to write one of these. I was trying to find some code, and I stumbled across WSQ 003's consistent hashing algorithm. And I was at once enamored with it. It was simple, powerful, reusable, beautifully crafted, and it was really close to being kind of an immediately reusable component. So what I decided to do is to fork that and put a whole bunch of comments in the code and turn it into a library and build some extra demos in the form of unit tests to show how the consistent algorithm developed by WSQ 003 works. Parenthetically, I have no contact information for them other than their GitHub site. So if WSQ 003 is out there, I hope you don't object to my taking your work and adding some comments and some other things to it and presenting it. It's a brilliant algorithm that deserves to be used and shared, and it's very clever. And if you object to that, please let me know. If you can prove that you're you, I'll happily take all this down. I'm not trying to usurp the credit for WSQ 003. I'm trying to demonstrate how clever the implementation of their algorithm for this is and how powerfully reusable it is. The basic members of what the author wrote was a struct called byte to int32 converter that allows a set of bytes to be unpacked into unsigned 32-bit integers, which is an important function needed in the murmur hash. The murmur hash algorithm itself, which uses it, and I should point out that the murmur hash is not designed to be a cryptographic hash, right? It's designed to, given a key space, more evenly distribute the keys over the key space and to have the hashing be deterministic. So the same key should yield the same hash every time, which cryptographic hashing doesn't always do, right? In fact, it often does the exact opposite. Because the purpose of a cryptographic hash is to take a set of bytes and give them a unique fingerprint that you can use to determine if something's been tampered with. And that's one hash use case. But the other hash use case is generating hashes to be used in storing things. And that's what the murmur hash is designed to do. And you can go and look in the Wikipedia article and read all about murmur hashes. There's a couple of YouTube videos of murmur hashes that are really great. WSQ 003 came up with a particularly tidy and high-performance version of the Murmur 2 hash. There's also a Murmur 3 hash and a Murmur 1 hash, but for this purpose, a Murmur 2 hash is a pretty darn good compromise between hash key distribution and speed. Because one thing you want when you're trying to decide where to put something is you want it to be computationally pretty brisk so that, you're not wasting a lot of time in that necessary and important middle step, but, you are getting better results. And so it's nicely encapsulated in a static method called BetterHash, which takes a string and returns a hash. And it's a better algorithm than the traditional kind of .NET solution of taking all the members of a class and XORing them together, XORing their hashes all together. That's not a bad hash for comparing, for example, if two members of the same class are in fact the same value quickly. But it's not a good hash for distributing keys through space, which is what we're trying to do here. And then lastly, the consistent hash of T algorithm itself, which implements the consistent hash circle and deals with creating the consistent hash, adding and removing members from it, and so on. And the best way to understand that is to go and look at the code that does the demo. But these are the three elements that are in the library I made on WSQ003's behalf that I have annotated. I've also kind of modernized them a little bit. They are C#9 on .NET Standard 2.1, so they should be reusable pretty much everywhere. And with that, okay, here's the first of the members that WSQ003 came up with. It's a byte to int converter struct. Notice that effectively what we've done is make a union in C# by using struct layout and having the offsets be the same. The upshot of that is when we use it in code in the murmur hash, we can effectively map an array of bytes onto the corresponding array of uints. So here is the hash algorithm. I've hidden away some of the bits and pieces, and you can follow this if you want, but I just wanted to show you that on line 45, there's just a really clever way of getting an array of unsigned integers from an array of bytes by virtue of using a union. And then the hashing algorithm, I'll let you decipher for yourself. There's a lot of interesting and very cool math in here. But effectively, the bit that we care about is this delightful thing called BetterHash. And BetterHash can be used in the override of get hash code to effectively get a hash code for a string on the fly using the murmur hash algorithm. Notice that here I've elected to use the default seed, but if for some reason the default seed isn't quite giving you the distribution you want, you can refactor this to use the seed of your choice. Here's a consistent hash algorithm of T, where T can represent the thing upon which you are hashing keys to. In other words, I'm trying to decide, given this key, on what thing to put it. In the demo code, there's a class called server that represents, some abstract thing. We're going to assign the workload with this key to this server. But T could be a class that represented a storage location or whatever you want. The point being that the consistent hashing algorithm keeps the consistent hashing circle as a hash index and then the thing it got hashed to using a sorted dictionary. Why a sorted dictionary? Because that will result in having a consistent allocation. There's also an idea called replication count, the implementation details of which are a little too complicated for this video, but you can go look in this algorithm and see how it's used. It's effectively a very clever way of making sure that we don't just have information in one place. One of the things that makes this algorithm faster is that it does store an ordered set of the keys, and then you can fire up your consistent hash circle by feeding it a list of the nodes that you want to represent your hash circle. In the methods area, we essentially just need two methods other than the constructor, one to add a node and one to remove a node. And then what we need to be able to do is say, well, given a key of blah, to what T should I assign it? So again, in our demonstrations, T is a server object, but it could be a storage cluster, it could be whatever. But that's the magic of this algorithm. And one of the things about this algorithm that I really like is that the implementation is nice and simple, that you can, without even understanding the nuanced detail of murmur hash or indeed even consistent hashing, you can implement this using its public methods and have a perfectly good consistent hash. So let's go and look at the sample tests. I am a firm believer that if you're trying to understand someone else's library, that the best thing that you can do is write some tests, because the tests allow you to have kind of mini scenarios of what should happen. We have three fundamental tests here. Map keys onto servers, map keys onto servers and then add some nodes, map keys onto servers and then remove some nodes, that demonstrate the power of consistent hashing. So let's go take a look at our base use case. So the first thing we're going to do is we're just going to make a bunch of keys. The library makes keys using a secure random key maker and a subset of the alphabet. And so you get key strings that have printable characters in them that are very thoroughly randomized. The regular out-of-the-box random might do a pretty good job too, but our implementation of secure random does an even better job, and the better the keys are randomized for this purpose, the better. I'll also point out that key length is a function. In any kind of hash mapping algorithm, the length of the input determines the reliability of the resulting hash, as does the length of the thing that you're storing to. If you're looking for a fairly reasonably even distribution, you have to play around with how big your key is and how many nodes you need to have. And in the case of this example, where we're actually using a server as the extemporaneous thing to store it on or to dispatch work to, there's an economic concern, which is I may math it out that I need 150,000 servers for really good key distribution, but there's no way the boss is going to pay for that. So you have to balance the trade-offs. And in order to do that, you have to understand the trade-offs. And one of the best way to understand the trade-offs is, write some tests that show what happens with different trade-offs. So this is the base algorithm that is going to be used in the other tests. And in the other tests, we're just going to add nodes or remove nodes and show you what happens. But it's worth spending a little time on this one in the sense that I'm going to go through and make a key item which has the key that is generated from the hash and the slot that we're mapping the resulting thing to. So slot refers to the index in our server farm. So I'm going to put it on server 0, 1, 2, 3, 4, 5. So here we are creating a little server farm. And again, the server class doesn't do much. It's just there to represent what we're hashing to. In this case, we're going to keep count of the number of times we hash something to it, so that at the end we can show you a little histogram and show you how the keys were distributed across the servers, and we can show you how that changes when we add and remove nodes. And creating a consistent hash, in this case I have set the number of replicas down to 10, and so this ch variable, right, consistent hash of server, is the consistent hash circle. What we have done is we've said, okay, our initial circle is going to be made out of, in this case, 10 server nodes with, in this case, 10 replicas. The next thing we need to do is roll through, figure out what server each key in our key ring, or key list actually, is going to map to. And we call that by calling the very easy to understand map key to node, which does a murmur hash of the key and returns the server. And then just for the sake of remembering where things go, I am assigning the result to the slot variable. And I'm counting the total number of items that were added to that particular server. The key is keeping track of what slot it was assigned to, and the server is keeping track of the number of keys that were assigned to it. So the first thing we're going to do is kick out the distribution of keys per server. And it's kind of a little text-based histogram. It's a little less than a histogram as much as it is a report. And then we're going to calculate some stats on the distribution, right? We're looking for a pretty reasonable set of standard deviations and averages. And then we're going to run through some random test samples of the keys. And in fact, confirm that our consistent hashing algorithm maps the key to the slot it mapped to before, right? And if it doesn't do that, given that we haven't changed the number of servers, it should be 100% perfect match in a consistent hashing algorithm. That's the consistent part. This is the printout, essentially the little histogram that shows what the distribution of keys to servers was. And you can see we've got some low spots and some high spots, but the average and standard deviation are not that unreasonable. But more to the point, it shows, since there are no exception messages down here, that when I remap that same key set back onto the server ring, that I got exactly the same answer each time. So this proves that the base use case works. Okay, everything was as it was above, except this time I have a different assertion block and I have a different piece of logic. In this case, I am adding 2 new servers to the server ring. The reason I'm adding 2 is it's a more significant disruption to our consistent hash than just adding 1. And it makes it a little more obvious. And then what I'm doing is I'm doing the same sort of test sampling and saying, okay, how many of those had to get moved as part of adding 2 more servers? In other words, when we're going around the consistent hashing circle, we go, well, really, this key should now map to this node instead of that node. So let's take a look at that. We'll go ahead and run this. So here's the output of that test. And you can see that some of the keys got remapped to new nodes. 2 went to 11 for that particular key, but a lot of them stayed essentially the same. So if we look at the summary on the very bottom, it should tell us out of the total of 1,000 key mappings, only 18 of them had to be moved. That's pretty low impact in terms of maintaining the distribution of keys across your server pool. Again, everything is the same as it was above, except in this case, we're going to remove 2 nodes instead of adding 2 nodes. And then we're going to do the exact same analysis where we randomly pick a bunch of the keys that are in our key list, and we see how many of them had to be redistributed since nodes 2 and node 7 don't exist anymore. So here you can see that most of the hashes stayed the same. For the things that hash to servers that don't exist anymore, they got remapped. And notice that they get remapped backward. In other words, it finds, because it's going around the circle clockwise in ascending order, and then when it gets to the maximum going back to 0, right, that remapped keys fall back to the previous node. So if we go all the way to the bottom of this and look at the analysis, we can see that, again, very few keys out of the 1,000 keys needed to be remapped. Only those keys that were assigned to nodes that no longer exist have to be moved. And that is the hallmark of a really good consistent algorithm. Kudos again to our invisible friend who wrote this algorithm, and I hope you enjoyed this. You can reuse this library. It's published up on NuGet. Thank you for your kind attention. If you like this kind of content, please do consider subscribing and giving us the thumbs up.